Today, we'll talk about polar bonds and acid and bases, particularly about organic compounds. Why? Polar bonds is very common bonds in most of organic compounds, and they can the polar character can explain several different kinds of chemical reactivities. Also, many organic acids and bases has the covalent bonds, and they covalent character of the organic acid and bases can explain acid-base property based on equilibrium constant. And organic acid and base plays very important role in many organic reactions. Bond is a bond between two atoms. Depending on the distribution of electrons between two atoms, we can classify those bonds like a covalent, or polar covalent, or ionic. If two electrons are completely on one atom between two atoms, then we call ionic, like a Na plus NCl. But two electrons are equally distributed between two atoms, then we call completely covalent bond. If two electrons are shifted to one of two atoms, then we call polar bonds, polar covalent bond. Ionic bond has a charge, +1 or minus. Covalent bond, in the covalent bond, the atoms are neutral because they are two electrons are equally distributed. But if they are shifted to one of two atoms, then one of two atoms will have a positive character and the other atoms will have a negative characters. So let's say positive character we show like a delta plus, and delta, negative characters like a delta minus. If they have polar characters, one atom has delta plus and the other atom has a delta minus, so we can draw a vector of the charge between two atoms, and we can define the dipole moment between two atoms. Dipole moment is defined by number of charge multiplied by the distance between two particles. But the dipole moment is a vector quantity, so it has a size and also has a direction. For example, the water molecule has two non-bonding electrons, and non-bonding electrons will have negative characters, but hydrogens will have a positive characters. And you have two bonds between HO and O and H. And we can draw two vectors between HO and HO, and we can add up these two vectors, and the result, final vectors can be represented like this. For a methanol, you have 1, 2, 3, 4, 5 bonds, and each bond has each dipole as a vector quantity. You can combine all those vectors and you can draw the final sum of all those component vectors, and it can be represented like this. Ammonia also can have a dipole moment. Actually, you can calculate it if we know the charge, and try to pay attention to the unit of Debye. In this case, the unit of Debye is Coulomb meter, because it is defined as charge multiplied by the distance. Okay, the unit of charge is Coulomb, and unit of the distance is the meter. And so the 1 divide equals to 3.336 10 to minus 30 coulometers. Each atom has a certain number of electrons in the outermost shell. But when they make a bond, sometimes when they make a bond, the number of electrons in the outermost shell is not the same as the neutral atoms. If they are short of electrons compared to the neutral species of the neutral atoms, then it will have positive charge. If the atom has more than the number of larger than number of electrons that they had in the neutral species, then they will carry negative charges. The charge represented by an atom by drawing structures is called formal charge, right? And it's strong. It will be determined by the number of electrons surrounding the atoms and number of electrons in the neutral species, neutral atoms. For example, in these molecules, the carbon has 4 electrons around the carbon atoms, so it's neutral. However, sulfur has 1, 2, 3, 4, 5 atoms, 5 electrons surrounding sulfur. The number of electrons of the sulfur in the outermost shell in an neutral atomic state is 6. Therefore, sulfur will have a +1 charge. Oxygen has 6 electrons in the outermost shell for a neutral species, but in this bond, it has 7 electrons around oxygen. Therefore, it has -1 charges. And we can easily, after draw the chemical structures, we can easily deduce the formal charge of each atom in the molecule. There are some more examples here. In this case, CH3 NO2. In this case, nitrogen has +1 charge, formal charge, because if you count the number of electrons around nitrogen is 4. Actually, the number of nitrogens if you look at the atomic tables, the number of nitrogens in the outermost shell is 5. Therefore, is +1. Oxygen is -1. Methyl phosphate, it has a formal charge of -2 for the molecules and 2 minus charge on the oxygen atoms. Just to count the number of electrons and try to understand the formal charge of this species. It's a summary of the formal charges. Okay, you count the balanced electrons around the atom, and count the number of bonds, and number of electrons. You add up the number of bonds and number of electrons if they are the same as the balanced electrons in this neutral species. Okay, it's short of the balanced electrons, then it will have positive charge. It has extra electrons compared to the balanced electrons, it will have negative charges. Okay, so look at this table and try to understand it. Even though we draw the structure using the lines and dots like this, however, the electrons are very small particles, and you cannot see it. Also, electron is so small, has dual property. Sometimes it behaves like a particle, small particle. Sometimes it behaves like a wave. If it behaves like a wave, it's not an actual particle. Okay. So even if we draw the structure using the lines or a dot, that doesn't mean the electron is actually located in 2 atoms. Okay. Also, and the location of electrons can be represented only by the probability. For example, If we have a CH3NO3, we can write the structure on the left side. But also, we can draw another structure which satisfies all the octet rules. The real structure of this molecule will be between these two structures. The structure on the left side has negative charge on the oxygen on the bottom. Structure on the left side or right side has a negative -1 charge on the oxygen on the upper side. But the real structure will be like this. Two oxygen atoms probably may have 0.5, -0.5 negative charge, even though the nitrogen will have a +1 charges. So the real structure of this molecule will be like NO, and there is a partial bond between NO, and there is another partial bond between NO. So actually the bond character between nitrogen and oxygen will not be a one single bond, it will not be a double bond, it will be like a 1.5 bond, okay? Another example is the benzene molecules. You have 6 carbons connected to each other, make a ring, but all these six bonds are the same. So actually, the real structure will be like all the 6 bonds is 1.5 bonds instead of 2 bond, double bond, single bond, double bond, single bond, double bond, single bond. It's not a correct representation of these molecules. Okay, so there are many other examples for the resonance forms, and this each component of the structure in this case is called the resonance structure. So the real structure can be represented by the combine of all these component resonance structures. And it is important to draw all kinds of resonance structures, all kinds of possible resonance structures. In this case, this molecule is an organic acid. If you add the base, it will generate a negative charge on the carbon like this. You can move the non-bonding electron on the carbon and draw the resonance structure like this. Okay. This is a red card species. You also can try to draw the resonance structure of this, right? But when you draw the resonance structures, make sure you follow the octet rule, okay? So far we talked about structure and bond and polar bonds of the organic molecules. And then many organic acids and bases has a polar character, but they can behave as an acid or base. So we'll briefly review the concept of acid and base and apply to the organic molecules, okay? The common concept of acid and base can be explained by the Bronsted-Lowry and Lewis. The Bronsted-Lowry acid and base is defined as a proton donor as an acid, proton acceptor as a base, and Lewis acid is defined as electron acceptor, and electron donor is defined as a Lewis base. Actually, these two definitions, they are not. They are deeply related to each other. Actually, the concept of Lewis is more extended concept of an acid base compared to the Bronsted-Lewis acid and base, because in Bronsted concept, the proton donor is an acid. Because the proton donor is an acid, the proton donated by a molecule will be an electron acceptor because the proton is positively charged. Proton acceptor is a base. In order to accept the proton, the molecule should be electron donor because the proton is positively charged. therefore, the Lewis concept is a more generalized concept for acid and base compared to the Brunstad-Lowry. This is an example of a Brunstad-Lowry acid-base reactions. It's an acid, obviously it's an acid. HA is an acid, and HB is a base. And the example is acetic acid is an acid, and H3 is a base. We can try to think about the reaction between CH3COH as an HA and H3 as a base, okay? In the ionization of organic acid, we can represent the equilibrium constant, okay? The neutral molecule can be ionized as H plus and A minus. So we can define the equilibrium constant like a Ka as H plus multiplied by A minus divided by HA. To the little mass, to the use the log functions, and you can convert the equilibrium constant equation easily to pH equals to pKa plus log HA, A over HA. What does that mean? This is called Henderson-Hasselbalch equation, and this means pKa is constant. pH, you can adjust it. If you add protons, the pH will be decreased. If you add OH minus, that's a base, and then you will see the increase of the pH. Because pK is constant, by changing the pH of the solution, you can automatically change the relative ratio of neutral species and negatively charged species in an acid. And also this pKa represents the strength of an acid. The higher the pKa, the lower the acidity is, okay? So there, table 2.3 explains the relationship between pKa and acidity, right? Out of this, there is oh wow. In this case, most of acids, acetic acid is an organic, ethanol is organic acid, but HCl is the inorganic acid. The typical organic acids are very weak acid. That means equilibrium constant Ka is much smaller than 1. Because the Ka is smaller than 1, pKa will have a positive value. For example, acetic acid has the pKa 4.76. That means equilibrium constant is 10 to minus 4.676, right? So very small portion of acetic acid will be ionized. Methanol and acetone has much higher pKa. That means the acidity is much lower. And we can also consider this acidity in terms of the equilibrium constant, okay? And this explains why this explains the difference of the pK in several organic molecules. The first one is methanol. If you ionize, it has a negative charge on the oxygen. For acetic acid, it has a negative charge on the oxygen, but it can be stabilized by the anode resonance forms. That's why acetic acid has lower pKa. For an acetone, this is acetone. For an acetone, the pKa is smaller than acetic acid, but it is larger than the methanol, right? Yeah. Oh, yeah, it's smaller than, larger than the methanol. That means it's weaker base than the methanol, and it's weaker. Weaker acid than methanol, and weaker base than weaker acid than acetic acid. Here are some examples of organic bases. The common feature of organic bases that those molecules contain non-bonding electrons on the heteroatoms. like nitrogen, oxygen, like that. I told you that methanol is an organic acid, but in this case, you have a number of electrons on the oxygen. Sometimes it can behave as a organic base also. Okay, so depending on the reaction partner, it could be it could behave as a acid, or it could behave as a base. I just briefly explained the concept of the Bronsted-Lowry and the Lewis concept on the acid and base concept. Lewis definition explains that base is an electron donor and the acid is an electron acceptor. In order to be an electron donor, you need an non-bonding orbitals. In order to be an electron acceptor, you need a vacant empty orbitals to be filled by the electrons from the other molecules. Okay, so we can easily understand the definition of Lewis acid and base based on the concept of orbitals, whether they are filled orbitals, filled non-bonding orbitals, or whether they have vacant empty orbitals. Vacant empty orbitals will accept electrons, so it will behave as a acid. Non-bonding electrons in the non-bonding orbitals will behave will donate electrons and behave as a base. Here is an example. PF3 is a Lewis acid, and diethyl ether has a non-bonding electrons, two pairs of non-bonding electrons on the oxygen, and behave as a base, right? So it can undergo acid-base reactions and make a complex. That's the salt, right? There are some molecular models which can easily explain the relationship of the special relationship of atoms in molecules. Easy to understand. So far we talked about the single molecules, but in practical way, we never talk about the single molecule. We always talk about a bunch of molecules. Like 1 mole of the molecule contains 6.02 multiplied by 10 to 23. So whenever we talk about some molecules, then the molecule will behave as a group. Therefore, the interaction between molecules or interaction among molecules will play a very important role to determine the physical or chemical property of the molecules. That's why we talk about the non-covalent interactions between molecules. Okay, we can in this textbook covers the 3 different kind of non-covalent interactions. Actually, this is intermolecular interactions, all right? Dipole-dipole force and dispersion force and hydrogen bonds. Dipole-dipole interaction is due to the dipole moment I just explained previously. So the polar molecules will have a dipole moment. If those molecules are close to each other, then there will be interaction between molecules, that is the intermolecular interactions. Dipole is a vector representing by the charge, so it is very straightforward that there is an interaction between molecules due to the dipole moment. If you have a strong dipole moment, there will be a strong electrostatic interactions between molecules. Dispersion forces means if you have molecules with a large number of electrons in a molecule, those electrons constantly moves. So sometimes the electrons is shifted to the left side, or sometimes electrons shifted to the right side. Those shifting of electrons in a certain time will create charge, like here. If one molecule have this charge induced, this induced charge, then it will create induction of opposite charge on the nearby molecules, like here. This induction of a nearby charge will create interaction between molecules, okay? And we call this as dispersion forces. Hydrogen bonds, hydrogen bond forces is the hydrogen bonding force between hydrogen bonding donor and hydrogen bonding acceptor molecules among the molecules. Like water molecules, you have hydrogen bonding between water molecules, or ammonia molecules, you have hydrogen bonding. Okay, because you have water has a hydrogen bonding donor and hydrogen bonding acceptor. We can think of many other hydrogen bonding donor and hydrogen bonding acceptor molecules. If they mix together, then we can imagine the hydrogen bonding between two molecules. Just like a DNA helix has a very strong hydrogen bonds between bases of the DNA, between bases of the DNA chains, and makes the DNA double helix stronger. Now, this chapter explained the importance of polar bond of the organic molecules, and applied this polar character for acid-base characters of the organic molecules. Polar character which determine the electronegativity difference of two atoms, and also plays important in the dipole moment. And valence bond and non-bonding electron determines the formal charges. Also, the real structure of the organic compounds can be represented by the combination of several resonance forms. And finally, explained Bronsted-Lowry acid-base concept. Rank the following substances in order of increasing acidity, okay? So acetic acid is the stronger one. The smaller the pKa, the stronger the acidity is, right? Okay, this is the end of this chapter.